Hi, my name is Rishi Pathak. This is my presentation for Lab 2. I've titled it Observing and Analyzing the Motion of a Ping Pong Ball in Free Fall. So a quick introduction to the premise of this lab. Essentially, the purpose was to determine the true extent of the drag force on the falling object by determining the drag coefficient for that object. This concept is pretty important, as if an object is not greatly affected by air resistance as it falls, it will continue to accelerate faster than an object that is affected. A good example of this is a parachute, which slows down the acceleration of a falling mass quite greatly and prevents it from accelerating further once it reaches a terminal velocity. The fundamental principles involved in this lab were the position update formula, Newton's second law, and the velocity update formula. The turbulent drag force was also used. This essentially says the drag force is directly proportional to the square of the magnitude of the object's velocity. The experimental setup was as follows. I used a standard ping pong ball with a standard mass and diameter. During the fall, the non-negligible forces that acted upon the ball were the force of gravity and the drag force. These are shown in the free body diagram to the left. The origin was placed at the ball's center of mass in the starting frame. The starting frame was said to be at a point after the ball had left my hand, as it was impossible to determine when the ball had truly left my fingertips. The initial velocity was found by measuring the change in position across the initial and second frames and dividing by the time elapsed. Here is a video of the ball falling. As you can see, I defined the x-axis as going horizontal with the positive x pointing to the right, and defined the y-axis as going up and down, with negative y going down. In order to better understand the effect of the drag force, I developed two models. My first model assumed that the drag force had zero magnitude. I set the initial conditions as shown in the slides. I set the initial conditions as shown in the image above. The proportionality constant was also set to zero. I also assumed that V average equals V final. This was an adequate assumption, a safe one, as delta t was 1 times 10 to the negative third, which is a very small value. The no drag model is shown here. The second model assumed a drag force existed. After setting the initial conditions as described in the picture above, I determined the drag coefficient to be 69 times 10 to the negative fifth. I found this by trial and error, editing the value until the final position of the model lined up with the final position of the experimental data. I again assumed that V average was equal to V final. Here's a picture of the drag model. In order to examine whether the ping pong ball, if allowed to fall for a greater period of time, would eventually reach a final constant velocity in both the models or just one, I graphed the velocity versus time for a period of 5 seconds in the models. My data showed that the model that accounted for drag force eventually did reach a point where velocity was constant. This occurred as the drag force increased as the velocity increased until the net force became zero, and thus the velocity remained constant. However, this does not occur for a situation without drag. Additionally, I examined if the same terminal velocity would be reached if the ball possessed a non-zero initial velocity. By modeling a situation where the ball started at a non-zero zero velocity against one where the ball's velocity was zero and then graphing both situations, I found that the final terminal velocity was actually the same. So this occurs because the drag force's magnitude depends solely on velocity of the object instead of the time it has been falling. Thus, it will equal the gravitational force at the same velocity for an identical object. This means that the terminal velocity for every object is always the same, as the gravitational force equals the drag force at the exact same velocity. And now finally, a quick discussion of the results. It was actually really surprising to see how much the drag force influenced the motion of the ball. By plotting the experimental position along with those given by the models, I found that only the model that accounted for the drag force closely predicted and modeled the experimental data. The slight discrepancy shown between the experimental data and the model that accounted for the drag force was likely caused by human error when tracking the ball's position, or an error in the precision of the drag coefficient, as there may have been more numbers that would have followed in order for the model with drag to accurately model the experimental data. On the other hand, the model that did not include drag modeled the position of the experimental data quite poorly. This mostly occurs because the model fails to account for the slower acceleration of the ball as a result of the drag force. This illustrates that ping pong balls actually experience significant air resistance.